keynote speech. And this year's speaker is famous BSD guy, Losher. And let me let me introduce him briefly. Losher is a senior operations architect at the Internet System Consortium based on Redwood City, California, USA. He has over 15 years of system administration experience, including almost 10 years development, maintaining worldwide DNS deployments. This includes root servers.net, one of the 13 DNS root servers, and ISG's new secondary name service, SNS at ISG. So, Peter, please get started.
Okay. I'm very happy to be here. Many of you, especially in the FreeBSD community, know me from basically the hosting services we provide for the FreeBSD and NetBSD projects, and the fact that I like to break developers on a semi-regular basis. But my day job is basically at ISC is to basically operate DNS servers worldwide, as well as just do general DNS operations. So in the last, probably about last 3 years or so, we've had a revolution basically in how DNS works, between rolling out IPv6, adding quad A records everywhere, especially at the root. We're coming across IDNs fairly soon, internationalized domain names, and but probably the most important one that has come down the pike or come down the line has been DNS security. So what my presentation is mostly talking about is DNSSEC in particular, and why we need it, how it came about, how have we started to deploy it, as well as some of the challenges that the OS vendors are going to have to basically support DNSSEC coming soon. So what I'm not going to talk about, which maybe you may or may not expect, is I'm not going to go through and talk to you through how to sign a zone and so forth. There are many tutorials on the net that actually describe that, and that would be a whole nother talk. So, okay. So as I said, I'm going to go through what is DNSSEC, how does it work exactly for the end user, especially as it pertains to a recursive server, because that's where mostly the end user is going to see it. A little bit of background history. We didn't get it right the first time, as with most things. And along the way, even when we got the specification correct, there were some pitfalls that came across. But in the last couple of years, we've seen the light at the end of the tunnel with finally an agreement to sign a root zone, as well as talking about deployment scenarios, as well as for the OS vendors. And then I'm going to talk a little bit about the next steps going forward. So, what is DNSSEC? DNSSEC is a set of IETF extensions for DNS, which gives DNS the resolvers and clients the ability to verify the origin of any DNS response. It was developed to protect the internet, or protect DNS resolvers from forged DNS data from things like DNS cache poisoning, which I'll talk about briefly in a moment. So, expressly, what it does, it provides origin authentication and protection for DNS data, as well as a means of public key distribution. So you can actually look up a domain name, or look up for a reverse domain name, and basically verify that you are getting the correct information, because there will be a signature associated with it. But what it doesn't do is it doesn't provide confidentiality. So it doesn't protect data, it just authenticates that it exists. And, oh, by the way, while you're re-architecting DNS, make sure it doesn't break backward compatibility, which is always hard. So why do we actually need DNSSEC? The reason is because basically right now, DNS is very, we trust it. You look up the domain name, say www.isc.org, and you get an address back, an A record or a quad A record, and you implicitly trust that response. There's no verification. You believe it's the correct address, and this is the way that we've operated DNS since the last 25 years. However, there are people out there that aren't so nice, and as described in RFC 13 or 3833, it does describe the sort of security risks in the current DNS infrastructure, and with mostly resolvers, and how they can be compromised, and that's what we call cache poisoning. So cache poisoning is basically a case where a resolver asks for a, say, www.isc.org, and it sends a request out to the authoritative server. Now, there could be a malicious DNS server, sends back a response, says go to 1.2.3.4, which is a malicious website that has some Trojan or so forth, and it sends it back before you actually get the response, the real response back from the authoritative server. Now, the reason you could get away with that so relatively easily was because most DNS servers would run between port 53 on the resolver and port 53 on the authoritative server. So they're running on the same ports. So all you'd have to do in that case is just basically match the query ID, which is only 16 bits. So you could throw a whole bunch of traffic at the recursive server hoping that one of those query IDs would be correct. And if it was correct, the recursive server would accept it and then put it in its cache, because for performance reasons, obviously, recursive servers cache their data for an X amount period, depending on what the time to life is of the zone. So it would have that, what we call poisoned record inside the cache, which would consider the cache basically poisoned altogether. So it couldn't be trusted. So we've done things over the last decade to try to minimize this. The latest being the response to the Kaminsky vulnerability, as many of you may know. What we did in that case, it was port randomization, where basically the client or the recursive server sends out a query to the authoritative server, but while the authoritative server is still doing port 53, the recursive server is sending it from some high port, and it's randomized. So besides the query ID, you also have to figure out which port it actually came from, so you can send it back to that same port to enter into the cache. Now, in theory, you can still actually beat it, but you basically have to throw at least 10 megabits of data, or no, 100 megabits of data for about 2 days to actually break it. So we figured by this point, you're probably the IDS intrusion detection is probably noticing the high traffic flows coming from the outside going to this one IP address, and probably your net flow will probably shut it off. But it is possible, but it's very hard to actually exploit. So you basically have to be on like the same network or something like that to actually get that sort of throughput to actually exploit this. But that being said, that's basically the last bullet in the gun that we have to sort of fight this, because you want to maintain backward compatibility, but we can't add more ports to the port randomization technique. So we need something whereby we can actually authenticate the data that's coming back is authoritative. That's basically the only real solution to this cache poisoning problem, is that we need to make sure that the answer we get back is the right one. So how does it actually work for the end user? So as I said before, we use we use public key cryptography. Boy, I'm having a hard day. To assign answers to DNS requests. So we use public keys. There's basically in the DNSSEC world, there's a KSK and a ZSK key. The KSK is kind of like the ZSK is basically the key you use to sign your zone all the time, and the KSK is kind of the secure portion of it, and that's what you keep on your or keep on the upstream. And so there is a key exchange mechanism as a part of DNSSEC, as part of the infrastructure, and so we use that to actually digitally sign our answers. And what we do is that all the records show up as you have your A record or your quad A record. The quad A record has its what we call an RR signature, so RR sig resource record, and the A record has also an RR sig record, and they're independently separate. So each record has its own RR sig associated with it for verification purposes. So all queries to assign zone will serve the original request. So say I serve, as I'll give an example, plus the RSIG record associated with it that it then can use to validate against. Now, a resolver that is configured to validate those DNSSEC records can then determine if it was the correct answer, i.e. if the answer was secured. So here's the process in gratuitous detail. So the resolver asks for the quad A record for, let's say, www.isic.org. Since the resolver is configured to validate responses, it sets the DO flag in its request, which means DNSSEC-OK, which tells the server that please send me the RSIG data, and hopefully I'm eDNS compliant. And I'll talk about eDNS compliance in another slide. Now, the resolver then gets an answer and tries to validate it by querying the root server for the relevant DS and DNS key records and validating it via an out-band trust anchor. Now, what I mean by trust anchor is that in this scenario, you will have the trust anchor in your named.conf or similar configuration file for the DNS software that you're using. And now you'll download that either via HTTPS or it'll come with your DNS software distribution. So when the root gets signed, we'll be able to set a root trust anchor in your named configuration or your bind or DNS software configuration. Sorry, I'm not trying to be too bind specific here. So you'll have that in there. So it's not something that automatically downloads off the internet and just updates. Now, you may trust what your software gives you in that respect, but you also have the option to download the trust anchor, whether it be from ISCDLB or whether it's from ICANN or IANA for the root zone. So it's something that's actually there in your configuration file that it uses to at least bootstrap the verification process. So then when it contacts the root server, it then will verify it against the trust anchor that's in your configuration file. Then it just follows the normal DNS path, verifying along the way. It starts with .dot, goes then to org, looks at the org signatures, verifies that they're correct, then goes down to isc.org, verifies those records are correct, and then can then verify www.isc.org. Now, if there is no RSIG record for www.isc.org, or there is a missing DS or DNS key in a chain, whether it be in org, whether it be in dot, whether it be in isc.org, then the chain's broken. So it then can't verify the path. And you'll get a validation failure and get an insecure response, which can be set one of three ways: insecure, bogus, and indeterminate. So how did we get here? There we go. So back in 1990, Steve Belvin found some serious flaws with the DNS infrastructure as it was then, and published a paper in 1995 basically going, this is critical infrastructure, this is really insecure, it really needs to be fixed. So the IETF started work on addressing these issues, and RFC 2065 was created in 1997, and then several revisions by 1999. RFC 2535 was thought to be a working solution, and then we started implementing it. That included ISC with bind. It was in 9.1, I believe, was when we implemented the original DNSSEC spec. By 2001, however, we started finding scaling issues, especially when it came to key changes, because it required a 6-message protocol and numerous data transfers of keys, because we were storing them as SIG records. So every time there was a key rollover, all the records had to be updated. So this might be fine for, say, someone like ISC.org who has maybe a couple of hundred resource records. For someone like org or com, where they have 20, 30, 40 million records, this causes a problem, because there's a lot of data transfer going between, say, the subdelegations and the parent while they're trying to change their keys back and forth. So you could basically DDoS your own servers by your children. So it just didn't scale. It was one of those situations where it sounded really fine in the lab and in development and in committee. When you got finally into production, it just fell flat in its face. My company can take blame for it just as much as everyone else. So the original DNSSEC was shelved, and work started to find a more scalable solution. So what came about was RFC 4033. So it's called DNSSEC-BIS to just differentiate it from the original protocol, but in most parlances that we just call DNSSEC. It's the one that everyone uses now. Nobody uses the original specification. The major change here is that when a child zone, as in like someone under org, ISC.org, changes, instead of having those 6 messages per record, there's now just one, where the child zone sends its public key to the parent, and the parent just only stores one key related to that zone. So there's only the initial key exchange, and that's it. No multi-6-part dance and twist around and sacrifice a chicken, blah, blah, blah. So even though we finally decided, okay, this is what the DNSSEC specification will entail, there were still some deployment issues and some pitfalls along the way. One of them is the packet size. Now, with DNSSEC, responses were always going to be bigger than 512 bytes. In the DNS world, 500, you always try to keep your responses or your DNS traffic always under 1 UDP packet. That was the holy grail. In the early days, when we started rolling out Quad A records for the root zone and for DNS servers, we get a whole bunch of registries would start shortening their names of their name servers to try to squeeze as much space as possible for the long IPv6 address, just so they can keep their DNS packets inside 512 bytes. So this was a big thing for us, because it's like, no, we can't have UDP fragments, the world will end, blah, 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 blah. And so with DNSSEC, it was just avoidable. You just couldn't avoid it at this point, because as you can see with the example up here, I'm doing a dig plus DNSSEC for www.isc.org's Quad A record. And so what I mean by that is I want its answer and I want its RRSIG. So as you can see, the actual response of the Quad A is its usual short IPv6 address. But then when you include the RRSIG, it then blows up to a received message size of just over 1K. So that's never going to fit into a 512 byte UDP packet. So what the IETF developed was eDNS, which is basically to allow larger UDP sizes to carry this additional information. So as I said, when you do a response for DNSSEC, you set the DO bit that says, okay, please send me eDNS tracker, please send me something bigger than 512, I'm fine, go ahead. And it was, eDNS 0 is set for DNSSEC. In theory, there will be an eDNS 1 and eDNS 2 if we ever need it. But for DNSSEC, it got eDNS 0, and it was codified in RFC 2671. So, okay, we found the solution to the problem. We can deal with bigger than 512 bytes. So, what happens? Why haven't we deployed already? Well, there were some problems. Device support. Home gateways, little devices, your little NAT boxes, Cisco PIX firewalls. All these machines have been hard-coded in the past to say all DNS packets are always under 512 bytes, and we'll just drop them otherwise. And then you've got the misfit toys. It's just people have deployed things out in the field that have worked for years and years and years, and people have forgotten them and until they break, and so forth. Now, when it comes to the discussion why we haven't rolled out a root server yet, is because there was a big discussion about, oh my God, we'll break the internet, because all these devices that haven't been configured to accept anything bigger than 512 bytes will just drop packets, and the whole internet will crash. So as I say here, that without the wide deployment of eDNS, what will happen is that resolvers will fall back to using TCP. And for that will cause additional load on the authoritative servers, because we have to process all the TCP traffic, and it's more resource intensive, and we have to start tuning TCP to stop dropping packets, or don't keep my sessions on for so long, and things like that. So the deployment was basically put off while we tried to get vendors to put out fixes and updates and so forth, and to start allowing eDNS traffic. There's one at Cisco for the fixed firewalls and so forth, and so it's just taking time for that to be deployed, and at a certain point we say, okay, we're either going to do this now or we're going to do this never, because you're always going to be paralyzed by the person saying, well, you'll break the internet because there's this mom and pa have not upgraded their home gateway, and they use a DNS proxy, and all of a sudden their traffic will fail. So you can actually check to see if you're behind such a bad device by using, there's a reply size tester. It's basically you just run a dig command against a address provided by the DNS OARC folks, and it will give you a response, and I'll show you an example here. So this is the results from the hotel network that all the speakers are staying at. So I just do a dig against rs.dnsorg.net, and text just means it'll send me back the text records that it generates after running the test. So basically it's saying that I sent an eDNS buffer size of 4K, which is the max, and gave me a timestamp, and then said that the reply size limit is just under 4K, which is fine. As I showed in the previous example, most answers in RSIGs will basically be just over 1K anyway, maybe 2K. So it looks like the hotel network will survive just fine with DNSSEC. The other one I tested was here.
Yeah, I just tested it too.
Yeah. So this is what you don't want to see. Basically, it's set to basically drop anything that's bigger than 512 bytes when it comes to DNS. So it says the DNS reply size limit is at least 490. And it notes that it lacks eDNS support and defaults to 512. Now, from what I understand, it looks like these devices are doing DNS proxy. I don't know if it's these Cisco wireless devices or not. and it goes off to IIJ's name servers, who's the provider here. I'm pretty sure that IIJ knows how to support the eDNS. So I suspect what's happening is the DNS proxy here is actually doing the limiting. So it's the intermediary NAT device that's actually causing the problem. So I don't know if there's any way to tell the local wireless folks that they should change that. Or it's probably just a simple firmware fix in most cases. So another problem that came up was a term called walking the DNS tree, or zone enumeration, or zone walking. There's several names for it, actually. So zone walking is the process of learning the contents of the zone via repeated queries to the authoritative server. So it's somewhat similar to basically query bombing the whois server for a particular domain name or a particular TLD to figure out what are the valid domain names registered under that TLD. So to either use a spam or spamming them or harvesting what are the available domain names so domain squatters can squat on the zones and so forth. So most of the big TLD operators actually don't allow things like zone transfer, where you can just transfer the whole zone and then you can parse it and so forth, which for researchers, kind of like some of us at ISC, is a bummer. Some of the bigger zones actually allow you to zone transfer it, but it's only under NDA and research purposes and so forth. And it's sort of a similar case with the root zones. F is actually still the only root server operator that allows you to zone transfer the root zone. So we actually, under DNSSEC, it's actually easier to do this zone walking process because of the NSEC records that are introduced as part of the specification. The NSEC record lists two names that are ordered canonically. So order to show that there is nothing that exists between the two names. So you can go via the whole set of NSEC records to list all the names in a zone. It's trivial with modern computing power to basically enumerate the contents of the zone for querying the names that don't exist. So if they don't exist, so you can basically distill the actual zone file by just doing the zone walking. So unfortunately, many registries don't allow the copying of the zones, as I said, with zone transfers, whois bombing, or anything like that, because they don't want domain squatters trying to suck up all the zones. Alternatively, for privacy reasons, especially with some of the European TLDs, they're subject to EU privacy regulations, and depending on how they're interpreted, it could be seen as privacy theft if you're able to walk the zone and figure out data about how many domains are registered or who they're registered to or things like that. So the use of these NSEC RRs are basically a no-go for them because it just exposes them to too much, it exposes them to this domain walking issue. So as a response to this, there was much arguing on the relevant IETF groups about how to fix this, because for a lot of people it says if you stick your information in the DNS, of course it's public. There's no such thing as private DNS data. So what's the beef? Well, of course, the TLD operators come back and say, no, we've got these regulations that we have to stand by. Most famously, our DENIC folks think, or DENIC friends think that's a violation of the German privacy laws. So they could be, in theory, fined or put in jail for basically exposing this data. So after much deliberation, RFC 5155 was developed, which is DNSSEC hash authentication denial of existence. I love this wording. So
in this scenario, a DNSSEC aware server can give, instead of an NSEC response, an NSEC-3 response, which is signed when the record isn't found. And instead of using the actual name in the response, it's hashed with an optional salt, raising the computational time needed for enumeration. So basically, crack me, please. So that's what's actually happening with a lot of the bigger zones. Org was not signed until NSEC-3 support was actually rolled out in bind. We know that's also the case for .at, .de, .uk. A lot of the bigger CCTLD zones were waiting for NSEC-3 support to actually get out there before they would sign their zones. So it was a big hurdle to get this in the code and get it in fast so we could increase the deployment scope. So a lot of the early ones just went ahead with NSEC, with the original NSEC spec. But you were never going to get the big players, the orgs, the COM, the net, and the big country code TLD operators unless this was actually put in place. This was actually a big barrier. So, light at the end of this long tunnel. Now, as I said, we started working on this in 1995. So, IANA, which is actually managed by ICANN, actually has been signing the root zone on an experimental basis since 2001. There's actually a website where you can download the signed root. It's not the same one as what's actually being rolled out now, but for those that wanted to test the signed root, they could actually download the trust anchor and download and zone transfer the zone and be happy, joy. So in the fall of 2009, after much layer 9 thru, which I will not go into, ICANN, VeriSign, and the US government agreed to sign the root zone, or agreed to a process to sign the root zone, which was signed by the end of 2009. Why haven't you seen this yet? The reason is because we're currently rolling it out across all the root servers in an incremental process. This process with dates and more explanation is actually laid out at the URL up on the board. And basically the reason is because it is a massive change to the DNS. We're now going to roll out signed root. There is still the issue of bad devices that may act wacky. One of the things we really wanted to research was how much of an increase were we going to see in, say, TCP traffic. And because we are going to see it, that's just inevitable. It's just a matter of how much. And so as we roll it out, we wanted to see if, because they wouldn't manage, they couldn't manage eDNS, that they would just migrate to another root server. So would all the other root servers that didn't have signed zone as it rolled out would get increased traffic. So it was a way to kind of see how the process would go, and then if we saw anything really, really odd, we could back out and start over. Although in reality, if we had to start over, this would probably never ever happen again. It's kind of one of those one-time opportunity deals where everyone has finally decided, okay, let's finally do this. Because actually what removed this logjam was the Kaminsky vulnerability. It finally shook the US government it shook the US government to shake the relevant parties that, yes, we should really sign the root now because we need to really have authenticated data. Because if people we don't want people who are trying to go to www.irs.gov they want them to actually get to the IRS website and not to some offshore government facility or pseudo-government facility that will just take their money. So, so currently, right now, the signed root as it's being rolled out is not validatable. That's on purpose. We don't want anyone to actually stick in trust anchors for the signed root, and then if we have to pull it out, then the trust anchors will be invalid and they'll start getting server fail everywhere, and that would be just a bad thing. So, so we call this the DIR zones, deliberately unvalidatable zone. And so that's getting rolled out. We'll be seeing it in early April. I think it's April 12th. is the actual week we're doing it. We're one of the last ones because we have a rather large Anycast installation, so they decided to put us near the end. So, but if all that goes well, and actually if we see anything in regards to this testing, we'll see it probably when we do it, because by that time there'll be just 1 or 2 letters of the root servers that don't have this zone yet. So if anything funky is really going to happen in regards to traffic, we're probably going to see it then. So the last server that's going to get this is JRoot. And if we start seeing JRoot's traffic just skyrocket because all these bad devices that can't handle eDNS are just going to run to J, then we're going to see it then. So we'll know there's going to be a month period between the final cutoff and then the final when we turn on the fully validatable signed root. And in that point, we're still going to serve the DERs unless they roll it back for some reason. And so on the 1st of July, we'll be told, suck this zone across, and it'll be fully validatable, and they'll probably be on that website, they'll probably list the trust anchor, and at that point you'll probably see bind or ISC included in bind in the bind configuration, as well as I assume the folks who make packages for all the various distributions and OS vendors will probably do the same thing. I suspect Barton will do it for FreeBSD, and whoever does it for NetBSD and OpenBSD. So the one thing you do have to watch out for, though, for those of you who do maintain the packages, try to keep up to date with the trust anchors. We did have a situation recently where a Linux distribution vendor, which I shouldn't name, actually put in a trust anchor for Write, which was out of date. And so when Write pulled the trust anchor, all of a sudden all these all these installations that had this particular package all of a sudden started getting server fail, and was actually DDoSing the servers in question because they were going, hey, where's that signature? Where's that signature? So it really behooves everyone who maintain packages, please keep those up to date if you include them. Otherwise, just put pointers in for where the administrators can actually pull down the zone so they can manage it. I know it's a sort of a chicken and egg problem when it comes to that, but do you want to make it really, really easy for someone to just roll it out, or do you want to kind of be responsible for the fact that the administrators still have to then after the initial installation, they have to still maintain that trust anchor, whether it's for ISC DLV, whether it's Write, whether it's the root zone. So for deployment, I'm going to only cover for the DNS software the open source, the major open source software. For bind, 9.3 was the first one to support DNSSEC-BIS, which is the version 2. 9.6 is the first to support NSEC3, which is what I'm actually rolling out across all my servers at the moment. 9.7, what I didn't put up here is 9.7 is what we call our DNSSEC for Humans release, where we actually simplified a lot of the DNSSEC administration, like key signing, key rollover, managing a signed dynamic DNS zone, which is a real headache before. So for those of you who are interested in actually doing DNSSEC for your zones, I highly suggest looking at 9.7. It is a .0 release at the moment. 9.7.1 should be coming out in the next probably couple months or so. We've been busy pushing out bug fixes for that trust anchor problem that I just mentioned before. So NSD, that's the authoritative side. They do support DNSSEC records and so forth, so they will pass RSIGs and DS and DNS key. Same thing with Power DNS. Unbound, sort of the recursive side of NSD, well, not NSD. NSD and Unbound are both managed or both offered by the same company, NLNet Labs. NSD is just the authoritative side. Unbound is the recursive side. And the Unbound was basically written to handle DNSSEC validation. So that will handle it out of the box, just like mine does. Power DNS, their recursive server side, they are starting to work on DNSSEC validation, but it's not quite there yet. So as someone asked, is my country on this list? So the TLD, and what I mean by RIR is regional internet registries, basically the ARIN and RIPE, LOCKNIC, APNIC in this side of the world, AFRINIC, and so forth. So currently deployed, we have Bulgaria, Brazil, Switzerland, Czech Republic, .gov, that's in the US, Liechtenstein, .org, Puerto Rico, Portugal, .museum, Namibia, Sweden, Thailand, Turkmenistan, don't ask me why, that one was an odd one, and .uk. Now, note when I say .uk, I do mean .uk. Now, I don't mean .co.uk or .gov.uk, so it's just the top level. They haven't actually filtered it down to .com or .co.uk, and the subdelegation is quite yet. So for a lot of these countries that are in that similar situation, it's just really easy to actually just sign that zone because there are very few records and no one really has domain space in there, so it's a great easy way to do a test bed. As I said, there are some that are still testing because of the NSEC-3 issue. That include Austria, Germany, France, Japan, Mexico, Netherlands, Russia, and Taiwan. VeriSign, after much kvetching, had announced last year that CommonNet will be signed using NSEC-3 in 2011, which will close a large gap. And for the RIRs, ARIN and RIPE both sign their another ARPA zones that they get delegated from ICANN, or from IANA, I should say. So if you want to do a reverse lookup in any of the ARIN or RIPE address space, you will find that they are signed and they have RR6 everywhere, and life is generally good. So you can actually, if you're in the US and you have a .org domain, you can validate both forwards and backwards. So as part of the turn-up process and trying to get DNSSEC deployed, ISE had come up with a intermediate step to sort of spur the process on, because it was one of those things where you're never going to get critical mass unless the big boys do it, and the big boys weren't necessarily going fast enough. When I mean big boys is the VeriSign and the TLD operators and so forth. So we need to find a way to sort of get the grassroots involved in the process and trying to exercise, because part of the problem is that the specifications were done in not necessarily in ivory tower, but done in the lab, and we were trying to find ways of getting sort of production experience with this code. So one of the things we came up with, and it was an idea proposed by Paul Vixie and David Conrad and Sam Weiler, was this thing called DLV, DNSSEC look-aside validation. It was basically a way to have an intermediary handle the verification process. Since the root, we didn't know when the root was going to be signed at the time. It could have been 3 years, 5 years, 10 years. It provides an additional entry point from which to obtain DNSSEC validation. So basically, you stick in what basically is an additional trust anchor for DNSSEC in your name.conf in this particular case, and just say look-aside validation on, and then trust dlv.isc.org, and here's the dlv.isc.org key. So we actually run a registry, and we also slurp in the other sort of similar registries, or what are called ITARs, like IANAs, RIPEs, and so forth, to basically pull in all their zones. And we run a registry for individuals or organizations that are in TLDs that aren't signed yet. So say you're in COM or NET, and you just don't want to wait for VeriSign to allow you to sign your zone or submit your records up, you can just stick them in DLB, and then for the community who has DLB enabled, they can validate your zones just fine. We're in there. I think we're about 2,500 registrations, and I think that comprises about 4,000 zones. So, so in that particular case, what we're trying to do, and I should point this out because there are a lot of people spreading vicious rumors that we're trying to take over the root as an ISC with DLB, because it's basically, ooh, here's an alternate root path, you can validate this way. That was never, ever, ever the case for us. The process is that once the root gets signed and once TLDs are assigned their zones, and also allow you to upload your encryption keys via your registrar. So you can type into www.gandhi.com or joker.com and put your keys in just like you would your name server addresses. Once you can do that, we'll happily tell you to get off. That's our plan. Like with .org, everyone asking why we haven't kicked off all the .org people is because currently .org is a friends and family where you can insert your records. You can't just do it via your registrar yet. Once that happens, we're perfectly happy to tell people, please upload your keys to your signed registry and we'll close your account. Because we really do want to turn this off at some point. We do realize that it will probably be around for like another 10 years because there will always be these islands of TLDs that won't sign their zone for whatever reason. But hopefully in the next couple of years, most people will be off of it, and it'll just be there for those islands of non-signed zones. So it was helped to spur DNSSEC deployment. We had several issues that came up because of DLB that squashed some DNSSEC bugs. So it has been very, very instructional for us as operators and developers of DNS software. And for those of you who do want to register, the address is up there to how to sign up. And I highly encourage you to do so. As for web browser support, currently right now there's only a Firefox plugin, and it's marked as developmental, so you have to click an extra box to actually install it. Basically what it does is when you type in www.isc.org, when it gets the address back, the plugin actually makes it does the additional validation for you and checks to see if there is an RSIG record, and then as well as to basically do the validation. So you'll get a orange key if it's able to find the RSIG record, but then can't validate it because either your local resolver doesn't do validation or for some other reason. If it gives you a green one, it means it found the RSIG record, but yet, and also was able to actually validate it via your recursive server. So that's currently a sort of stopgap way. We're hoping that with the signed root, hopefully we'll be able to get some traction in regards to the web browsers to actually be able to have I don't know whether it's going to be a key or something else to go with the lock with SSL certificates. But it'll be some way to identify that this is actually secured via DNSSEC, however that is, and it'll be a core product or core option for, say, a Safari or a Firefox or Internet Explorer, so forth. So now, for the OS vendors, it's all nice and dandy to have web plugins and so forth that have DNS software that actually does this validation. The problem is that we still have things like get host by name and so forth, which have no capacity to know when the address it gets back has actually been validated. So for things like hostfix or sendmail or links, or say I want to do in FreeBSD package add -r, how can I validate that the answer I'm getting back when I give it a URL is actually the right address? So there's, from our perspective, now from, I have to remember which hat I'm wearing right now. ISC is highly encouraging folks to try to, we're not trying to impose a solution on you. We just want to pose the question, so at least it gets thought of. So what do we want to do with get host by name? Do we make a new get host by name? So to not break backwards compatibility, to handle things like DNSSEC, so it takes the DO response and says, yes, this is the answer, yes, the DO bit has been passed, so we can actually say that, yes, this address, this response has been verified. So as part of that, 9.7 does come with a updated libDNS library that actually comes with DNS Software, get adder info and get name info, which could be used as a possible replacement. There's also other options like LDNS from MNL Labs. So there are other 2 or 3 other projects that are trying to come up with validator libraries, whether they're GNU or BSD or whatever. So I'm just here to actually try to open the conversation and say, how do we get this information, this vital information, as far as I'm concerned, about getting the fact that the responses you're getting from your local resolver has been validated. So you can actually, if you want to be even more security paranoid, say, if I don't get an answer back that isn't validated, throw me an error. Because hopefully we'll get to a point where these records will be more ubiquitous than SSL certificates. And and no, we're not doing link encryption here. This is just authentication and verification. So the next steps. For all you projects, please sign your zones. I really do want to do a package ad or whatever and be able to verify that the address I'm getting back is actually the real one. A good tutorial can be found here. The only caveat I would make is that this one was written before 9.7 came out. So for 9.7, I would suggest downloading it and looking at the readmes and so forth. For those of you who are interested, you can email me. I will be happy to give you my card. And I apologize if I don't answer right away, but I will answer you in regards to this. There is actually currently a DNSSEC in 7 minutes presentation that we actually do give out, but we just redesigned our website and I could not find the URL. It seems to have gone. So, but I'll be happy to try to find it and send it to you if you want. Please turn on DNSSEC validation on your resolvers. For right now, I would suggest using ISC's DLV registry until the root is signed in a couple months. And then after that, you can also, when the root is signed, you can actually use both. You can use the root signature, and then you can use DLV for those zones that haven't been signed yet, like COM and NET, and .de or .jp. So you can have more than one trust anchor in your configuration. And we need to work to make various libraries and utilities DNSSEC aware. So if I FTP to a site, I want to be able to verify that the address I'm getting is verified. And same thing with package add, because we're doing a lot of things with binary packages and so forth. The thing that really disturbs me is that with bind, we've signed bind with our PGP or PGP or GPG key for the better part of a decade. And in FreeBSD, I'm not trying to slag Barton, really I'm not. We download the PGP key, there's no verification on it. No one runs a verify, it's just downloaded. And the one time we did break, because we used the wrong key at the time, we got 2 people who actually complained. And that's rather disconcerting. If there was really a Trojan file on somewhere, I mean, yes, you can try MD5 and SHA-256, but at some point, computing power will overpower even both of those. Or actually has with MD5. So I think this is a very important tool for verification because we're not, there are already issues out there with SSL certificates and so forth, and now you've got the folks like VeriSign who are putting out $500 enhanced SSL certificates, so you have a green bar on your Firefox screen. So I think this is a good solution, or DNSSEC will become a better solution to handle things like authentication and so forth. You still want the link encryption from your banking site, but you want to know that that is really your banking site. So I'd like to thank the organizers for asking me to come. I'd also like to thank ISE for basically saying, yes, please, go do it. Go talk about DNSSEC. And then thank all of you for listening. So I'm now open for questions.
If you find that 7-minute tutorial, would you please send the URL to one of the FreeBSD mailing lists?
Sure.
So, in order to change a get host by name, what you actually want to do is return a different style of hostnet. Right? So you're going to have to change. We're going to have to change the size of the hostnet, which is going to. It's a binary problem because the only thing that gets returned from any of the get host by names is that. But that's probably going to be the right answer, because if you create a new get host by name, no one's going to use it.
Well, yeah, it's kind of one of the
break the old one.
Yeah, I was talking to Paul about this before I left. It's like whether or not do we advocate changing get host by name and then breaking it for everyone else, or just doing a get host by name 2 and try to get people to migrate over to it.
So there already is a 2.
Oh, or 3.
It could be 3.
I'm perfectly happy with breaking it.
Yeah. Don't do a second get host by name. Just migrate to get other info. There's already a new one.
Well, that's why I said that we do have a DNS Software in 9.7 for libDNS, so which has those two. So as I said, I'm not here to basically advocate one specific method. It's just actually start the conversation and then have the BSDs or the various operating systems make their decision. As far as we're concerned, as long as you're passing the DO bit and passing the fact that it's validated, that's all we care about.
So I was curious, you mentioned that part of the rollout of DNSSEC depends on the registrars allowing us to upload our keys. I was wondering whether or not you were actually aware of, or if you could describe any kind of centralized effort to organize contacting all the registrars and getting them to fix allow us to do that kind of stuff.
Yeah. I mean, it's sort of similar to what happened with the addition of Quad A records to the root and adding Quad A glue. There are some registrars who still don't do that. I happen, at least the one I use personally, is Joker, and they do. And I believe Gandhi and some of the other geek-friendly ones are definitely allow you to do that. So I suspect there will be a sort of similar effort with the signed records. With .org at the moment, as I said, it's just basically friends and family. It's folks who know friends and affiliates who basically operate the registry on behalf of PIR. At some point, I suspect, once they allow it through their API or registrar interface, I think take-up will commence after that. I think it's just in a process that they haven't updated their API to the registrars, so the registrars can actually upload that information. Because I've actually contacted Joker, and they said just basically whenever the registry tells us we can. So I think that's where the intermediate process is. Once you give the registrars the ability to actually do it via their API interface to the registry, then I think you'll start to see it happen. But it's not going to be a case of all registrars will turn up at once. It's going to be sort of geek-friendly ones that will probably start first, and then you'll start going across to the corporate registrars and so forth. They'll just roll out like that. Anyone else? So I'll be here for the rest of the conference. So if you do have any questions and you want to bring up in private, I'm definitely open to it. And thank you very much for your time.
I just searched that. I couldn't help but laugh when I see this on the right-hand side.
So, Randall,
Half the side.
yeah, so you may have, that could be way changed.
It looks like it's the other one, yeah.
I was just about to check out the work. I also